Okay, so in this video, we will consider two key words in counting, and or. So let's start with the first, and. When we use the word and, what we mean is a sequence of choices. So we'll select something, then something else, then something else. And so it really represents a sequence of several choices. So you can imagine saying, okay, I choose the first thing, then the second, then the third, up to say the kth choice. So suppose you have a sequence of k choices. First choice, then the second choice, then the third, up to the kth choice. So we assume you have k consecutive choices, so a sequence of choices. And for each choice, we'll have a different number of possibilities. Suppose that for our first choice, we have n1 possibilities. So I'm using n1 for the number of possibilities of our first selection. This could be 5, it could be 100, it could be 2014, we don't know. But our first choice, there are n1 possibilities. Suppose that for our second choice there are n2 possibilities. For our third choice, n3 possibilities, up to our kth choice, nk possibilities. Then we're asking to count the total number of possible selections. Well, if you think of it, when you say and you'll see in a second, what you are constructing is really, again, a sequence of choices. But if you think about this in terms of set theory, this is just the Cartesian product of the sets for each choice. So what you have is a k-tuple of choices, and now we're saying, okay, there are n1 possibilities for the first choice, and n2 possibilities for the second choice, and 3 possibilities for the third choice, and up to and k possibilities for the kth choice. So what we have is simply a Cartesian product, and if you remember, when you have a Cartesian product and you want to know the total number of possible elements, you have to multiply the number of possible elements for each slot, for each choice, and this will give you the total number of possible elements, therefore the total number of possible selections. So we have n1 possibilities for the first choice, and times, and 2 possibilities for the second choice, and times, and 3 possibilities for the third choice, and times, and k possibilities for the kth choice. And so this is the total number of possible selections. And that's it for and. So when you say and in terms of counting, the implication almost always is that you have a sequence of choices, and if you are interested in the total number of possible such selections, so ordered selections, you simply have to multiply the possibilities for each selection, and this will give you the total number of possible such selections. So always think of it as and means multiplication. Well, what about or? Well, let's see. If you think of it, or stands for, again in terms of set theory, or stands for union, right? An element is an A union B if it's an element of A or an element of B. So or will stand for a partition. Imagine that you have just two sets of your sample space. Now there are two possibilities. there could be an overlap or not. Let's suppose first that there is no overlap. So we have our first set A and our second set B. And again, suppose you say we want to count the elements that are coming from A or coming from B. So it means that we have to add those elements with those elements. But again, the word or refers to union. So if you said I want to count the elements coming from A or coming from B, all you're really asking is the number of elements in the union between A and B. Well, if they are disjoint, so there's no overlap between A and B, this is a very simple problem. Add first all the elements of A, then add to this plus all the elements in B. And you're done. But there is a possibility that A and B could be overlapping. So what if we have now the following situation? Again, we're asking for the same thing, to count all the elements coming from either A or B. But now some elements are common to both A and B. Once again, we want the number of elements coming from A or B, so the size of the union. Well, if you think of it, again with the Venn diagram, well, first let's add all the elements coming from A. Then let's add all the elements coming from B. But if you notice, we're supposed to add all the elements coming from either A or B exactly once. But we've counted the elements in the intersection between A and B twice. To count those once, we have to remove them once. So if we remove the number of elements in the intersection between A and B, as with these two, we counted those twice. Removing it once, we're not counting everything just once. And that's it. So the lesson here is when you say or, you mean a partition of your counting, which means an addition. Except just be careful that when you're adding the union of two sets and there is an overlap, you must remove the intersection. So, our conclusion is quite simple. When you use the word and, the implication is almost always a sequence of choices, therefore a multiplication to get the total number of selections. When you use the word or, you mean a partition of what you're counting, which means an addition of the different parts. And that's it. So and, multiplication, or addition. Be careful that if there is an overlap, you have to remove the size of the intersection. Let's consider now an example of each, for and then for or. So this is an example for and. Very simple problem. A school cafeteria offers 3 different meals on Monday, 2 on Tuesday, 4 on Wednesday, 3 on Thursday, and 5 on Friday. How many possible weekly meal selections does a student have? Again, visualize the problem. We have to select our meal for Monday, then for Tuesday, then for Wednesday, then for Thursday, then for Friday. So we have an ordered selection of 5 choices. Our choice for Monday, then our choice for Tuesday, then our choice for Wednesday, then our choice for Thursday, and then our choice for Friday. Well, we have 3 choices for Monday. We have 2 choices for Tuesday, 4 choices on Wednesday, 3 choices on Thursday, and 5 choices on Friday. So if you ask, and again the question is how many possible weekly meal selections does a student have? So we're asking for the total number of possible such selections. An ordered selection of 5 choices. So the number of selections equals, and again read this out loud. We have 3 choices on Monday, and 2 on Tuesday, and 4 on Wednesday, and 3 on Thursday, and 5 on Friday. We're saying n every time. We have an ordered sequence of selection, and so we're just multiplying every number. So 3 choices on Monday, and times 2 on Tuesday, and times 4 on Wednesday, and times 3 on Thursday, and times 5 on Friday. And that's it. So if you multiply this out, here if you're clever, you do 3 times 4, 12, times 3, 36, and 5 times 2 is 10, 36 times 10 is 360. And there you go. Let's now do an example with OR. And at the same time with an OR, we'll also use AND again. This problem here is a little more interesting. So again, this will be mainly OR, but we will use the idea of AND again. So here's the problem. We consider a password consisting of 3 symbols. The first is an integer between 0 and 9, inclusive, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 10 possibilities. The other 2 are lowercase letters from the standard alphabet, so A, B, C, D through Z. We're asking how many possible passwords are there, A, in total, B, starting with a 2 or a 7, or C, starting with a 2 or ending with a Y. Okay, well let's start with A. And as always, try and visualize if possible the selection you're trying to count. So we're asking how many possible passwords are there in total. Well, our password consists of 3 symbols, and a password of course is an ordered selection. So we have our first choice for the symbol, our second choice, and our third choice. Well, the first symbol is an integer between 0 and 9. As we have just said, if you count 0, 1, 2, 3 up to 9, that gives you 10 options. So we have 10 options for our first symbol. The other 2 are lowercase letters from the standard alphabet, so A through Z. That gives us 26 choices. So we have 26 choices for our second symbol, 26 choices for our third symbol. And now, if you ask, well, how many passwords are there in total? Well, we have 10 choices for our first symbol, and 26 for our second symbol, and 26 for our third symbol. We're saying and, so we multiply 10, 26, 26. So it is 10 times 26 times 26, which gives us a total number of possible passwords of 6,760. And that's it. So the first example, part A, was just N. There's no OR. In B now, there will be an OR. So it'll be slightly more interesting. So we're asking in B, how many possible passwords are there, starting with a 2 or a 7? So let's visualize this in a simple Venn diagram. We have 2 events of interest here. A password starting with a 2 or a password starting with a 7. So we have those two events. The first question, is there an overlap? Can a password start simultaneously with a 2 and a 7? The answer is obviously no. So we have our two events, and they are disjoint, so there is no overlap. I'll call the first one S sub 2 to say the set of passwords that begin with a 2. I'll call this one S subscript 7 to say the password starting with a 7. And again, because a password cannot start with a 2 and a 7 simultaneously, both events of interest are disjoint. Okay, we are asking now to count all possible passwords that either start with a 2, so those, or plus start with a 7. So we have to add those two together. Well, let's add each one separately, and then, well, let's calculate each one separately, and then let's add them up. So S2. Again, let's visualize all the passwords starting with a 2. Again, there are 3 symbols. The first one is a 2. It has to be a 2. So here we have only one option. The first character is a 2, and that gives us one option. The other 2 symbols can be any given letter. So that's 26 option in each case. So the number of elements in S2 equals, well, we have one option for the first choice, and 26 for the second, and 26 for the third. So it's 1 times 26 times 26. That is simply 26 squared. Let's look at S7 now. Again, let's visualize those passwords. 3 symbols. Now the first symbol is a 7. So again, we only have one option here. It has to start with a 7. So there's one option for the first symbol. The other 2 symbols can be any given letter. So it's 26 options for the second, 26 options for the third. So the total number of passwords in S7 is 1 times 26 times 26, also 26 squared. So finally, we were counting the number of passwords in the union between S2 and S7. So we add S2, 26 squared, plus we add S7, 26 squared, and if you add those two, you get 1,352 different passwords. And that is our final answer. There are 1,352 different passwords that start with a 2 or with a 7. Finally, part C, and this one we'll see is a bit more interesting. We're asking for the number of possible passwords that start with a 2 or end with a Y. But if you think of it now, these elements, these sets, are not disjoint because a password can start with a 2 and simultaneously end with a Y. So there will be an overlap between our two regions. So let's check this out. So first event is a password starting with a 2. Again, we'll call this S sub 2. Passwords that start with a 2. And now passwords that start with a, that end, with a Y. So I'll call this E sub Y. Passwords that end with a Y. And as we have just said, a password can simultaneously start with a 2 and end with a Y, so there is an overlap. But once again, we're trying to count the total number of possible passwords in this region, as we are saying OR, which means the union. Well, let's start with looking at S2, but we already counted S2. So this is already done. So the number of elements in S2 is 26 squared. Let's look now at EY, the passwords ending with Y. Well, again, there are three symbols. What do we know? Well, our password ends with Y, so our last symbol has to be a Y. So there is only here one option. It has to be a Y. Well, the first symbol therefore can be anything. There are 10 options. The second symbol can be anything, 26 option. As the first is an integer between 0 and 9, the second can be a letter from A to Z. So, the number of elements in EY, we are seeing 10 options and 26 and 1, so it's 10 times 26, which is 260. But now if you think of it, if we add S2 to EY, we are counting everything once but the intersection twice. So we'll have to remove the intersection. Well, how many passwords are there in the intersection? So S2 intersecting with EY. Well, let's visualize those passwords. Those are the passwords starting with 2 and ending with Y. So the first symbol must be a 2. So there's only one option. It has to be a 2. The last symbol must be a Y. So there's only one option. It must be a Y. The second symbol can be any letter from A to Z. That's 26 options. So we have 1 and 26 and one option, which gives us 26. So the size of our intersection is 26. And now we're good to go. We wanted the number of passwords in this region. That is, of course, as we have said, the size of the union between S2 and EY. All passwords that either start with a 2 or end with a Y. And as we have just said, we add all the elements of S2, 26 squared, plus all the elements of EY, 260. But now this is now this. And we've counted the intersection twice. We must count it once. So remove it once, and you're back down to counting it once. And the number of elements in the intersection is 26. And if you calculate 26 squared plus 260 minus 26, you will have 910 different passwords that either start with a 2 or end with a Y. And that's it.